Welcome back. Today we will be talking about section 1.3, average rate of change and relative change. So our first definition today is the average rate of change. So the average rate of change of, we're going to say of y, alright, between t is equal to a and t is equal to b, we're going to say that y is equal to some function of t. Alright, so this is found to be the change in y, remember that's our delta symbol, represents change, over the change in t. Okay, and since y is a function of t, we can write this as the function value at our end point, remember t is equal to b, minus our function value at the beginning, which was t is equal to a, all over b minus a. Okay, so the average rate of change is actually the slope, alright, when we are talking about linear functions. We're talking about linear functions. Alright, but we can calculate the average rate of change for any function. Not just linear functions. Alright, so we're going to go ahead and jump into our first example, where we have the graph of a function g of x is equal to x cubed minus 2x squared, okay, and this is our g of x here. And the question asks us to draw a line segment between the points on the function where x is equal to 0 and x is equal to 3. So x is equal to 0 is down here. X is equal to 3 is over here, but on the graph, that's about here. Okay, and we're supposed to draw a line between these 2 points. There we go, something like that. Alright, we are asked to compute the average rate of change of g of x on this interval, 0 to 3. So the average rate of change of g of x on 0 to 3. Okay, so we have our average rate of change. Well, that's going to be our change in g of x over our change in x. So this is g evaluated at 3 minus g evaluated at 0 over 3 minus 0. So that's our g of b minus g of a over b minus a. So now we need to calculate g of 3 and g of 0. Alright, so we were given the function g of x is equal to x cubed minus 2x squared. So g of 3, I'm going to plug in 3 everywhere we see an x. So 3 to the third power minus 2 times 3 squared. So this is 27 minus 2 times 9. So we have 27 minus 18. And so g of 3 is 9. And then g of 0, well, that's 0 cubed minus 2 times 0 squared, and all of that just becomes 0. So g of 3 is 9 minus g of 0, which is 0, over 3 minus 0. We end up with 9 over 3, which is just 3. Okay, so we computed the average rate of change on this interval between 0 to 3. And then the last part asks us, what is the connection between the line segment and the average rate of change? Alright, well, let me give you these points. So here we know that x is 3. And in order to find our y value, we just needed to plug 3 into our function, which we did down here. So we know our y value is 9. And over here, we did the same thing. We know this point is 0, 0. So we have 2 points. That means we can find the slope, right? So our m value, this is our slope. And we know that's our change in y, 9 minus 0, over our change in x, 3 minus 0. And this is exactly 3, so it's the same number that we found above. So we have determined that the average rate of change between 2 points is the slope of the line that connects the 2 points. Alright, and we can look here and see that having a positive number makes sense because our function, well, our function is decreasing here, but then our function is increasing here, and it's increasing seemingly a lot more than it was decreasing. And so the average rate of change is basically saying, over this interval between 0 to 3, what is it doing more of? And here it says that it is increasing more. Okay, and so we have a positive slope. And so this was helpful for, say, you accidentally lost track of a negative or added a negative somewhere. And so you end up with a negative number, and you come over here and look at your graph, and you're thinking, but it seems to be going up a lot more than it's going down. And so then you can tell yourself, well, maybe a negative number wasn't right. We need to go back through and check our math. All right, well, that is example 1. So let's jump into example number 2. We have a different g of x function here. All right, and it's graphed below. And here we're asked to evaluate each of the following and then interpret them as the average rate of change over some interval. Okay, so part 1, we need to evaluate g of 0 minus g of negative 2 over 0 minus a negative 2. Let me see, we're using extra parentheses around here with those extra negatives. Alright, so we have function g, so we can go ahead and plug in these values to calculate. Alright, so let's do g of 0. Well, that's 1/16 times 0 to the 4th minus 0 squared, so that's just 0. Then we have g of negative 2, so we get 1/16 negative 2 to the 4th minus a negative 2 squared. This is going to be 1/16. Negative 2 to the 4th, that is 16. And then minus 2, negative 2 squared is 4, but it's minus 4. Okay, well, 16 over 16, that's 1. Minus 4, we end up with negative 3. Alright, so g of 0 is 0 minus a negative 3 over 0 minus a negative 2. That is going to give us 3/2. Alright, so it's asked us to interpret them as the average rate of change over some interval. Well, this is our B and our A as our interval, right? So the average rate of change over negative 2 to 0 is 3/2. Alright, let's go ahead and do part 2. So we have g of negative 2 minus g of negative 4 all over negative 2 minus a negative 4. We've already calculated g of negative 2, so why do it again? So we just need to calculate g of negative 4. Alright, well, we get 1/16 negative 4 to the 4th minus negative 4 squared. Alright, negative 4 to the 4th ends up being, so we have 1/16 times 256. Alright, minus 16 over here. 256 is evenly divided by 16, and it is 16. So then we have 16 minus 16, which is just 0. Alright, so g of negative 2, which we found earlier, was negative 3. So we have negative 3 minus 0 over negative 2 minus a negative 4. So we end up with negative 3 in the numerator. These two negatives become positive, so we have negative 2 plus 4, which gives us a positive 2. So the average rate of change remember this is B and A, so over negative 4 to negative 2 is our negative 3/2. So here we're doing decreasing more than we are increasing. Alright, so last part, g of 0 minus g of negative 4. Alright, and so then this will be 0 minus a negative 4. And we have done all of these calculations already. So g of 0 is 0. G of 4 is also 0, or g of negative 4 rather. And then we have 0 plus 4, so we get 4 in our denominator. So we have 0 over 4, and whenever there's 0 in the numerator, which is the top, it's just 0, no matter what the bottom is. Alright, so the average rate of change let's see, over the interval negative 4 to 0 is 0. And what that means, it was either constant and didn't change at all, or it went down the exact same amount it went back up between negative 4 and 0. And so it averaged out to be no change at all. So let's kind of take a look at this graph that we had above, because our second part to this problem says for each expression, draw the line segment on the graph whose slope corresponds to the calculated rate of change. So, our first calculation was on -2 to 0. So -2 to 0, okay, and we found our average rate of change to be 3/2, which is positive. And that makes sense since our function here is only increasing on this interval. All right, so if we want to draw a line on this interval with a rough slope of 3/2, we could say it looks something like this. Okay, so then our next interval was from -4 to -2. -4 to -2. And we found that to be -3/2. So, saying that it is decreasing. Okay. And then finally, our third calculation was over the whole area. It was over -4 all the way to 0. And it was 0, so it averaged out to be a net change of 0. We went down the same amount that we went back up, so they canceled each other out. All right. So example number 3 just asks us to compute the average rate of change for this function g of x on the following intervals. All right, so here we have a and b. So we need our average rate of change, and that's going to be our function evaluated at b minus our function evaluated at a over b minus a. All right, so g of 1, well, that's 2 times 1 squared. 1 to the power of anything is just 1. So we have 2 times 1, which is 2. And g of 0, well, that's 2 times 0 squared, and that's just 0. So up here we'll get 2 minus 0 over 1 minus 0. So we get 2 over 1, which is just 2. Okay. So then here we have a and b. We need our average rate of change. This is g evaluated at b minus g evaluated at a over a, or b, minus a. So we've calculated g of 1 already. That's 2. So we just need g of -1. Well, that's 2 times -1 squared. All right, and -1 squared is +1. So we have +1 times 2, which is just 2. So minus 2 over 1 plus 1. Alright, so we end up with 0 over 2, which is just 0. Same thing again, but now written a little bit differently. From x is equal to -4 to x is equal to +2, this is still our a and b. Alright, so we can go ahead and calculate g of b minus g of a over b minus a. Alright, so we need to do some more calculations. G of 2 is 2 times 2 squared, which is 8, And g of -4 is 2 times -4 squared. -4 squared is 16. 2 times 16 is 32. So we end up with 8 minus 32 over 2 plus 4. So we get -24 over 6, which gives us -4. All right, 2 more parts to this problem. From x is equal to a to x is equal to b. Well, that's g of b minus g of a over b minus a. But we can actually evaluate these functions at b and at a. So g of b, well, that is 2 times b squared. And g of a, well, that's going to be 2 times a squared. So we can write this as 2b squared minus 2a squared over b minus a. And we could simplify this a little bit more, but today we'll just leave it as is. So then we have from x is equal to a to x is equal to a plus h. So we need g of a plus h minus g of a over a plus h minus a. Alright, so g of a plus h, I'm just going to do it in line over here. Well, that will be 2a plus h squared, the whole quantity squared, so make sure you're using those parentheses. Alright, minus 2a squared all over, well, these a's and their denominator are going to cancel out, so we're just left with h. Okay? And again, we're going to leave it at that. So example number 4. The amount that Magdalena drives changes from week to week, so the amount that she spends on gas each week also changes. However, she has calculated that over the last year, she spent a total of $1,450 on gas over the last year. Okay, so our first problem is, on average, how much does she spend each week on gas? Well, we want to know how much she spends each week on gas. 1 year is the same thing as 52 weeks. Alright, so if we take our $1,450 that Magdalena spent in an entire year, and we divide that by the 52 available weeks in the year, and we put that into a calculator, we're going to roughly get $27.88. Right, and we can add a little dollar sign here. Okay, so on average, she spends $27.88 every single week on gas. If nothing major changes, how much should Magdalena budget for gas for the next 3 weeks? Well, if she spends roughly $27.88 on gas in 1 week, then she's going to need $27.88 for 3 weeks. Okay, so again, this is going to be about $83.65. And that is how much money she'll need for 3 weeks. Alright, so our next definition is something called the average velocity. And sometimes it's helpful to think of velocity as speed. Okay? So the average velocity is the change in distance So the change in distance over the change in time. So this is our delta D, delta T, and this gives us the average rate of change of distance, and then we like to use this phrase with respect to time. And usually that means something along the lines of per time or over time, and so that's us here dividing by the change in time. Alright, so we'll look at our first example with this information. So this is example number 5. And it says the speedometer in Andre's car is broken, but on the way to the store he was able to measure the distance from his house once per minute. The table below shows these measurements. So part A asks what was Andre's average velocity between the start of the trip and 3 minutes in. Alright, so our average velocity, we just said, was our change in distance over our change in time. Alright, so our change in distance between 3 minutes and 0 minutes. So distance is our bottom row. So that's 3,300 minus 0 over our change in time. Well, that's minute number 3 minus minute 0. Okay, so we just end up with 3,300 over 3, which comes out to be about 1,100. And then our units are feet per minute. Alright, because our time variable t is given to us in minutes and distance is given to us in feet. Alright, so Andre's average velocity between 0 and 3 minutes is 1,100 feet per minute. Part B, how about between minutes 2 and minute 3? Alright, so same thing, we need our change in distance over our change in time. Alright, but now we're looking at minute number 2 and minute number 3. So we have 3,300 minus 2,600 over 3 minus 2. So that is going to give us 700. Alright, so 700 feet per minute. And that is our average velocity between 2 and 3 minutes. So then we're given this graph down here below and asked to plot all of the data points on it. Okay, so let's do that first. So we already know 0, 0 is a point. At minute number 1, we're at 2,200, so somewhere over here. Then we go to 2,600. Then we go to 3,300. Then we go to 6,200. So we jump all the way up here. And 7,000. 7,200, and then 7,300. Okay, and if we wanted to connect these, it would most likely be something like a nice curve. Alright, and this is the average velocity, so how fast he's going between all of these points. Alright. Between which of the two data points is Andre's average velocity the largest? So between which points is he going the most amount of distance in the same amount of time? Well, that would be between minutes 3 and 4, right? He's covering quite an amount of distance there. And how about the smallest? Well, he's only covering 100 feet between minute 6 and 7 rather. So then we're asked to plot the lines between these two pairs of data points. So we've connected all of them with a nice smooth curve, okay? But now we need a straight line and a straight line. Because remember, if we want to find the average rate of change, well, that's the slope of those straight lines, okay? And the average velocity is an application of our average rate of change. All right, so using these 2 points that we've come up with, we need to find Andre's highest and lowest average velocity. All right, so highest, we said, was between 3 and 4. Okay. And so we need our 6,200 minus 3,300 over 4 minus 3. And that gives us that he was traveling at a speed of 2,900 feet per minute. Okay, and the lowest was between minutes 6 and 7, where we have 7,300 minus 7,200 over 7 minus 6. And so we just get 100 feet per minute. So at his fastest, he was going 2,900 feet per minute, and at his slowest, he's going 100 feet per minute. All right, our next definition is something called relative change. Relative change. All right, so relative change in some variable, we're going to call it P, is the change in P over P sub 0, which again is P naught, okay? And that's usually the original number, okay? And the change in P, well, that's just going to be the new number minus the original number, but then over the original number. Okay, and we usually express this as a percent. Okay, so good question. Why do we care about relative change? Well, let me give you this for an idea. If the population of New York changes by 1,000, all right, it's, I don't know how many millions of people live in New York, but I assume it's a lot. And so if it increases by 1,000 people, it's not a very significant increase. But if there's a small town with maybe about 1,000 people and its population increases by 1,000, then that population has now doubled in size, which is very significant. All right, so this is why we care about relative change. We're going to think about population sizes. Two different populations. So think about two different populations increasing by 1,000. All right, which one is affected more is essentially what we're trying to find. All right, so example 6. In 2017, YouTuber X had 1.5 million subscribers, and today the channel has about 2 million subscribers. What is the relative change in the number of subscribers of YouTuber X between these two data points? All right, so a relative change That is our P1 minus P0 over P0. Alright, so P1 is our new value, which we're going to say is our 2 million, minus our starting out value in 2017, which was 1.5 million, and then we need to divide this by 1.5 million. Okay, so we'll get 0.5 over 1.5, and if you put this into a calculator, we'll get 0.33, and that's repeating, so it's just going to keep being 3, 3, 3, 3, 3, 3, 3. Okay, we made a note that we usually express this in a percent, so this is 33%. Okay, so what does this mean? Well, 500,000 subscribers seems like a lot, but it's only 33% increase. All right. So that's what this calculation is telling us, that the YouTuber X's subscribers increased by 33%. All right. Example 7. During the first week of the semester at some local public school, the enrollment of Anina's business class went from 130 to 162, while Cortex's class dropped from 18 to 8. Which class had the higher relative change in magnitude? Okay, so maybe right off the bat you're thinking, well, 32 is a much bigger number than 10. So obviously Nina's class changed more. But what we're not taking into account there is relative to the number of students she already had. Alright, so let's go ahead and calculate our average or our relative change. So it's our new number minus our old number over the old number. So we get 32 over 130, which in a calculator comes out to be about 0.25. Okay, which we are going to say is a 25% increase in students. Okay, and then we have Cortex, where we have now 8 students, but we started with 18. So then we have negative 10 over 18, which in a calculator is about 0.55, but it's negative. So this tells us we had a negative 55% decrease in students. Okay, so the last part of this problem is which class had the higher relative change in magnitude, and that means ignoring whether or not it's positive or negative, which number was greater overall. And it's definitely our 55% here. So Cortex had the greater change in his student size. All right, example number 8. The puppy Sam bought for his girlfriend was originally priced at $980. He got the puppy on sale for $650. How much of a sale did Sam get? And adopt, don't shop. Anyways, so the puppy that Sam bought, okay, so our original price, so our new price is $650 minus our old price, $980, over the old price. Our calculator says that's about 0.33 negative, so we have negative 33%. So the puppy was on sale for, so the puppy was on sale for 33% off. Alright, so now we're going to learn about a new concept called concavity. Okay, so we can either be concave up or concave down. And what we mean by that is we've talked about increasing, decreasing, positive or negative functions. And now concavity has to do with which way the function is curved or bent. It doesn't need to be a full cup, it can just be some pieces here. These are all examples of a function that is concave up. Okay, and so then concave down looks like this. Okay, and if you need help remembering it, sometimes I write up like this, and I write down like so. So that helps you remember which one's concave up and which one's concave down. Alright, and we'll make a little note that a line is neither concave up or concave down. So example number 9 gives us this beautiful graph here and asks for which pairs of the consecutive points in the following function. Is it increasing in concave up, increasing in concave down, decreasing in concave up, and decreasing in concave down? Well, let's focus on the first part, A. So increasing in concave up. Well, we already feel pretty confident about increasing functions, right? So let's go ahead and label everywhere where our function is increasing. So we're increasing between A and B. We're increasing between D and E. We're increasing again between E and F. Alright, so those are all of our increasing areas. So now what about concave up? Well, A and B is not concave up, so we're going to go ahead and get rid of that. E and F is not concave up. So that leaves us with between D and E. D and E is where we are both increasing and concave up. Okay. So then we need increasing and concave down. Well, those will just be the other two areas that I erased just a second ago. So increasing and concave down, we have from A to B. And then union, this is just kind of an and symbol with E to F. Okay. So now decreasing in concave up. So everywhere we are decreasing, decreasing, and decreasing. Alright, well, F to G is certainly not concave up. B to C is not concave up. B to C is not concave up, but C to D is. So we're decreasing in concave up on C to D. So then decreasing in concave down, well, those would be our B to C and F to G. Alright, so B to C, union, F to G. Alright, and we've made it to our last example for today. Do we think we could use a table of values, shown here, to determine if a function is increasing or decreasing and if it's concave up or concave down. Well, to determine if it's increasing or decreasing, we just need to remember our definitions for increasing and decreasing, right? So if we're increasing, the values of the function f of t are increasing as t increases, and decreasing is the values of f of t are decreasing, but what was the catch? Still as t increases, right? Alright, so let's see what's happening here. T goes from 0 to 5, from 5 to 10, from 10 to 15. T is increasing. So let's see what happens with f of t as t is increasing. So we go from 12.6 to 3.1. That's an increase of 0.5. Then we go from 13.1 to 14.1. That's an increase of 1. We go from 14.1 to 16.2. That's an increase of 1.9. I'll go ahead and plug in. This is 3.8 increase. This is a 9.6 increase. And this is a 13.1 increase. So the function values of f of t are increasing as t increases. So f of t, or so the function f appears to be increasing. Okay, well that was the first part of the problem. Then it asks us, do we think the graph is concave up or concave down? So let's think about this for a second. Let's look at how much our function is increasing. Okay, at the very beginning, our function is increasing, but by kind of small numbers, right? And at the end here, we are now increasing by almost 10 and then 13. So kind of large numbers. Small, large increases, right? So if we maybe try to draw a picture of what this would look like, we know something that's increasing has to go up. Okay, but it's not linear because these increasing amounts are not the same, right? So it's not this line, but it's got to go up a little bit. So we're going to start here. We're going to increase a little bit at a time. So this is we're increasing by half, increasing by 1, increasing by 1.9. But then all of a sudden, we increase by 3, 9, 13. All right. So our graph might look something like this. And so what does this look like? This looks like f is concave up, right? Up. F appears to be concave up. All right, so that was our last example for today. Please feel free to email me with any questions and don't forget to take the comprehension quiz.